So in this video, we discuss the estimation of errors in numerical solutions, and more specifically when solving nonlinear equations. So as already became clear from the previous video, solving nonlinear equations is an iterative process, and the solutions that we obtain are approximate, but they can be quite accurate. Now, how accurate is accurate enough? So when do we stop these iterative procedures in which we get closer and closer and closer to the true solution? So how do we stop these iterations, and how do we define accuracy actually when we're doing these iterations? Well, accuracy, that implies that the error that we have, so the error between the true solution xts and the numerical solution x subscript ns, that is small. And in chapter 1 we discussed two main ways of defining these errors, and that is the total error, so the absolute difference in absolute terms of the true and the numerical solution, and the relative error. So here we use absolute value signs to make this positive always. But this relative error is normalized by either the true solution or the numerical solution, and this allows us to kind of judge how important an error is. Let's say an error of 0.1. Is that a bad error? Well, it is if that is on a solution of order 1, but an error of 0.1 when your true solution is in the order of millions is obviously not that important. However, a challenge here is that in these errors, the true solution, XTS, is not known. So computing both the total error and the relative error is actually impossible if you don't know the true solution. So the idea of quantifying errors is in the general case where no true solution is known to the problem. In the general case, this is kind of and it's impossible to do this. It's a kind of utopic idea that we want to achieve. And the best we can do is actually trying to estimate the error in an accurate manner. Now, there are different kinds of errors that we can define in this way. And we already know the true error and the true relative error, but we discussed that, well, because this true solution is not known, in most cases, well, the true solution is not known for any real practical problem unless you're working with really toy problems, because if you already know the true solution, then why would you even try to solve it numerically unless you're doing this for educational purposes? So this true error and true relative error are not known in virtually all practical cases, so we have to define different kinds of errors, so approximate errors. For instance, we can take a look at a tolerance in the function f of x. So recall that we want to solve the problem f of x is equal to 0. So we can check whether whether f evaluated at the true solution and f evaluated at our approximate solution, whether that is small enough, because that is an indication that x of the numerical solution would be close to x at the true solution. We also know that in the true solution, f of x is equal to 0. That is simply the problem that we're trying to solve. That's by definition, that is the case. So this one drops out. And we see that this tolerance in f is something we can compute. So that's simply our nonlinear function evaluated at the current estimate for the solution, x subscript ns. We can also try to look at the tolerance in the solution, so not in the function, but in the solution itself. And for bracketing methods, well, that's where we have this interval in which we are guaranteed that the 0 lies. The smaller this interval gets, the smaller the error that we can make eventually. So this size of the interval is also a measure for the error that we are making or that we're possibly making. So in bracketing methods, this would be a good tolerance on the accuracy of the solution. Or in open methods, well, there we have no interval where we are guaranteed that the solution lies in, but we can take a look at how the solution evolves in different iteration steps. So what we will typically see is that initially the solution is very different in iteration 1 and 2, and then again it's making a huge step from 2 to 3, but it's taking smaller and smaller and smaller steps as we close in on the numericals, on the true solution with our numerical approximation. So this tolerance in X for open methods is based on the difference in the numerical solution in successive iterations. And that can also be used as an estimate of the error that we're still making with respect to the true solution. Or we can also similarly define an estimated relative error to normalize this. And what we then do is, well, we just use this tolerance and we normalize this with the current estimate for the numerical solution. Now, each of these green errors can actually be used as a stopping criterion. So if the true solution is not known, well, each of these green error definitions can be used to assess how big the error is that we are still making with respect to the actual true solution using our numerical approximation. However, it's important to note that none of these error definitions is actually perfect. This can be, for instance, shown over here. So let's say that we have a function, a nonlinear function, x minus 1 to the power 7. And we are here at roughly x is equal to 1.25, so in between 1 and 1.5. Well, we know that the true solution to this problem is x is equal to 1, because that's easy to solve for us just out of sight. But at x is equal to 1.25, if we were to apply this tolerance in F criterion, well, we see that F is already extremely small at this point. So if we were to just base us on a tolerance in F, we might come to the conclusion here that, well, we attain quite a good accuracy using this approximate value of 1.25, where actually we are quite far from the true solution of x is equal to 1. So it's always a good idea to kind of critically assess your error, the estimation of your error, and the stopping criterion that you're using in your numerical methods.